Now, to better understand how to compute pre-stress losses due to creep, let us try to compute it in a sample problem. A pretension pre-stress beam has a span of 15.2 meters or 50 feet as shown. So this is the pre-stress beam with a tendon profile similar to this, which is actually a harp tendon, usually used for pretensioning as mentioned on the problem. And again, this is the this is the pre-stress beam, which is actually a simply supported beam, which supports a uniformly distributed load W. So the question asks for the pre-stress loss due to creep, given that the superimposed load, excluding the beam's own weight, obviously, because these are just the superimposed load. So when you say superimpose, these are loads other than the self-weight of the member or the concrete element itself. So the total superimposed load, according to the question, after transfer is 5.5 kilonewton per meter or 375 pound per feet. Assume that prior to transfer, the jacking force on the tendon was 0.75 FPU, which is actually the initial pre-stressing, the initial pre-stress that will be transferred on the concrete element. So this is actually the initial pre-stress that will be transferred to the concrete uh, at transfer. So other information about the concrete is the section at midspan, which is actually similar to this, with dimensions equal to this, and the distance of the pre-stressing reinforcement to the bottom is equal to this. And then other parameters given is the compressive strength, quantitative compressive strength, the initial compressive strength at transfer, the ultimate strength of the pre-stressing reinforcement, and the area of the pre-stressing reinforcement, which is actually 1/2 inch diameter 7-wire strand with an area equal to 99 mm squared or 0.153 inches squared. And we have 10 of those. And then modulus of plasticity of the pre-stressing reinforcement is equal to 186,200 megapascal. So to start for the solution, uh, we know that the formula for the pre-stress loss due to grip, according to ACI-ACE Joint Committee, is equal to this. So let us try to give the needed parameters to be substituted on this formula for us to be able to find the pre-stress loss due to grip. So let us start for finding FCIR, which is the stress at the level of the pre-stressing reinforcement at transfer with self-weight. So since the critical section here is at midspan, let us find the stress at the level of the pre-stressing reinforcement at midspan at transfer with self-weight stage. So this will be the formula for that: negative P over AC minus PEC. And since the distance of the fiber we are considering here to the centroid or neutral axis is just equal to the is just equal to the eccentricity of the pre-stressing reinforcement at midspan, we can use E in place of C, similar to this. Instead of using C, let us just use the eccentricity, because again, the fiber that we are concerned is at the same level as the pre-stressing reinforcement at midspan. So let us just use the magnitude of E. So the first thing that we need to find for us to be able to find FCIR, which is actually similar to FCS, if you can see this formula. So they are just pertaining to the same magnitude or the same value. So the first thing we have to find there is the magnitude of P, which is just the prestressing force that is being transferred to the concrete element when the prestressing force, the prestressing reinforcement is cut. So this is actually the prestressing force that is being transferred to the concrete. And we know that its magnitude is just equal to the difference between the loss due to the steel relaxation and the jacking force. But then again, since the question already specified the magnitude of this before transfer, which is just equal to 0.75 FPU, so we will just use that magnitude. And since we need a force, we must multiply the stress by the area to convert it into its corresponding force. So substituting the corresponding values, FPU is just equal to this. APS is 1099 mm squared. So multiply or substitute that here. And then for the value to be in kilonewton, we just have to divide it the product by we just have to divide the product by 1000 to make it in terms of kilonewton, since the product of these terms here are in terms of newton. So we just converted it to kilonewton. So the resulting value will be equal to this. So that will be the P, the initial pre-stressing force that we will use in finding FCIR here. So again, I hope you are not being confused by the symbol here. So this symbol here and this symbol here just signifies uh, same value, which is the uh, stress at the level of the pre-stressing reinforcement. So I hope you are not confused with that. So next will be the magnitude of M, which is equal to MDL for the stage of pre-stressing at transfer with self-weight. So we just have to get the magnitude of the moment due to the dead load or the self-weight itself at midspan, which is equal to WL squared over 8. Although we don't actually know the magnitude of W, but we can compute the magnitude of W by utilizing the unit weight of concrete. So we know that if you want to find W, we can use we can utilize the unit weight of concrete. We just have to multiply it to the cross-sectional area of the concrete. So with that, substituting the corresponding values, L is given 15.2 meters. Unit weight of concrete, as we all know, 23.54 kilonewton per cubic meter. Area of the concrete is just the product of the dimensions, 381 and 762. But we have to convert them into meters for consistency of units. So we must multiply this by, or we must divide this by 1000 as well as this. So a total of 10 to the negative 6. And then L is 15.2 given in the problem. Square it divided by all over 8. And then computing this fraction here, we can compute for or calculate for the magnitude of the moment due to the self-weight or dead load itself, which is equal to this. And then lastly, we need the magnitude of E, the eccentricity of the pre-stressing reinforcement at midspan, which can be computed if we will divide the depth. If we will divide the depth into half, or if we will divide to 2 the depth given here, so we will have a length equal to half the depth. And then if we will subtract the distance of the pre-stressing reinforcement from the bottom, then we can have the magnitude of the eccentricity of the pre-stressing reinforcement with respect to the neutral axis or centroid, which will be equal to this. So since we already know all of those values, we can substitute them on this formula. So substituting the corresponding values here on the formula and making sure that our units are consistent. So for consistency of units, we will just express the forces in terms of Newton. We'll just express this in terms of Newton, the area in terms of mm squared, moment of inertia, mm to the fourth, and the E terms of mm, and then the moment here we will express it in terms of Newton mm. So P will be equal to this in terms of Newton, area of the concrete multiply the dimensions of the cross section for pre-stressing force, copy, just copy, and then the magnitude of E is equal to this. So we have two of those. That's why it's squared here, divided by the moment of inertia of a rectangular section, which is just equal to BH cubed over 12. Base times height or depth cubed over 12, which is similar to this on this expression. And then the moment must be expressed in terms of Newton mm, so we have to multiply it by 10 to the 6. And then the eccentricity E. So computing those, the resulting stress will be in terms of megapascal or Newton per mm squared, which is equal to this. And we have a negative value here, meaning the stress acting at the level of the pre-stressing reinforcement at transfer with self-weight is a compressive stress. So that is actually the FCIR here on the formula here. So next with that, after that, we have to compute for FCDS, and according to the code, the ACI provision, FCDS is equal to this formula, wherein MSD is the moment due to the uh, total superimposed load. So again, uh, this is the moment due to the superimposed load or superimposed loads only. So you have to exclude the beam weight or the self weight or the dead load itself, which is actually the case given on this particular problem. So the 5.5 kilonewton per meter given here is actually the total superimposed load only, excluding the self weight of the concrete member. So we can just use that directly on finding this moment here. So again, the moment at midspan for a simply supported beam is equal to WL squared over 8. And we just have to use the magnitude of WSD to find MSD, which is just equal to 5.5 kilonewton per meter, which is given on the problem. Length is also given 15.2. So computing those, we will have this moment due to the total superimposed load only. Again, I will take note. You have to take note that MSD here is due to total superimposed load only. So you have to exclude the beam's own weight. And then the eccentricity of the pre-stressing reinforcement at midspan is already calculated here. So same E as we use on the calculation of FCIR. So we just have to divide the depth by 2 and then subtract this distance from the bottom of the pre-stressing reinforcement to the bottom of the concrete. And then substituting all of those here and making sure that we will have a consistent units. So we just have to convert the moment to Newton mm. So we have to multiply it by 10 to the 6. E we must be in mm, so it's already in mm. The moment of inertia must be in mm to the fourth. So we are consistent with the units, and the resulting stress will be equal to this. So all we need to do is substitute FCIR and FCDS along with EPS and EC. So what is the magnitude of EC? The modulus of elasticity of concrete. So if you will refer on ACI 318M-14 section 19.2.2.1 or on NSCP C101-15 section 419.2.2.1, you can see these formulas for computing the moment of, for computing the modulus of elasticity of the concrete. So we just have to substitute those here on the formula for EC here. And then lastly, for the value of KCR, since our concrete that we are concerned here is a pretension normal weight concrete, we assume that the concrete is a normal weight concrete since there is actually no given information about it. So if there is no given information, you just have to assume that it is normal weight concrete. And since it is pretension and normal weight, so we have to use a magnitude of 2 as the KCR, the creep coefficient. So substituting all of those on this formula, substituting KCR is equal to 2, and then the EPS, which is equal to this, and then the AC, which is equal to 4,700 square root of FC prime, which is this, and then the difference between FCIR minus FCDS, which are this. So again, you just have to disregard the sign for the FCIR, since it just pertains for the actual direction of stress, whether it is compressive or tensile. So computing this, we will have the actual magnitude of the prestress loss due to creep, which is equal to 66 megapascal. So that will be the expected prestress loss, or that will be the expected magnitude of loss of the prestress that is being experienced by the prestressing reinforcement as the creep of concrete occurs on this pretension member we have here. So that is how you can compute for the prestress loss due to creep.